Hi, I'm Gyuyeong from Sungshin University. So today, I've been presenting my work pushing the limits of in-network caching for key value stores. Key value stores are fundamental building blocks for modern online services like Twitter, Facebook, and Instagram. So they provide simple and fast data access and also require high performance, including low tail latency and high throughput. As we've got lots of data, the data is usually partitioned over multiple storage servers. One interesting characteristic is each key value item has different popularity. Actually, the popularity is extremely skewed. For example, if a famous singer posts the selfies, the likes will be over 10 million easily. But if I post the photo of my cute dog, the likes will be only 2 or similar. Actually, it will be much better. So this is not surprising because most people usually view popular content or trending posts. So at a system level, this skewed popularity means that only a few servers with a hot item receive too many request packets. So this skewed popularity results in load imbalance between storage servers, and this degrades the performance significantly. So addressing load imbalance is a key challenge in scaling key value stores. In-network caching, originally proposed by NetCache, presented in SOSP several years ago, is a great idea for load balancing key value clusters. The idea is to leverage the network switch as a load balance cache node. By leveraging the flexibility of the programmable switch ASICs like Intel Tofino, so that we can absorb the request to the hottest item, so the skewed workload can be balanced. So this is based on a very interesting theoretical result that we need only a small number of cached items to balance workload. So specifically, we need O and log n hottest item. Here, n is the number of storage servers or partitions, not the data size or the number of requests. While in-network caching is a great idea, NetCache has a significant drawback. That is, NetCache can support items up to only 16-byte keys and 128-byte values. Well, key value items are indeed small. Keys are usually tens of bytes, and values are usually hundreds of bytes. But the supported size by NetCache is too small compared to that of the production workload. We analyzed the public data set of Twitter workload and found that NetCache can't cache even a single item for many workloads. So the question is, how can you enable variable length in network caching? Well, to do this, we first look into the switch architecture first. In the programmable switch data plane, we have several match action stages. Each match action stage contains the statically allocated memory space and few ALUs for simple arithmetic operations. Packets go through these match action stages, so we can put our custom packet processing module by leveraging the resources of those match action stages. So in the NetCache architecture, the switch fragments the item value over multiple match action stages. So the request packet gather the fragmented values by going through a number of match action stages. So if we have 8 match action stages, and by assuming that each stage can handle 16 bytes, it means that the switch can cache 128-byte values. The size in the key size limitation comes from the fact that NetCache used the match action table to implement the cache lookup table. So there is the maximum key width of the match key of the match action table. So in the NetCache, item key is the match key for the cache lookup table. So that's why the NetCache supported only limited key size. We argue that it is hard to realize variable length in network caching if we stick to the concept of caching data in the switch memory. This is because the n times k constraint is logged in when switch hardware is manufactured. So we want to cache data in the switch data plane, but we should not cache data in the switch memory. Then the following question will be, where should we cache data instead of a switch memory? OrbitCache answers to the question. So OrbitCache is a recirculation-based in-network caching mechanism. So the idea of OrbitCache is to keep cached items circulating in the switch data plane by leveraging packet recirculation. Recirculation is a built-in feature supported by commodity programmable switches that makes the packet visit the switch data plane again. So the switch can process the same packet several times. So you can see that here, since the cache packet contains the whole key value pair, there is no fragments, no size limit, but the data is still in the switch data plane like this. So the cache packet is recirculated over and over again. This shows the difference between the netcache and OrbitCache architectures. So in netcache, requests read the cache data in the switch memory. Unlike the netcache, in the OrbitCache architecture, circulating cache packets read the stored request metadata. Not surprisingly, there is a trade-off in OrbitCache. That is, we should limit the cache size, because if we put too many cache packets, the recirculation port will be performance bottleneck. But fortunately, this can be backed by the small cache effect that we need only a small number of cached items to balance skewed workload. And the current switch hardware has enough capability to accommodate those tens of items simultaneously. So there are several technical challenges to translate the idea into a working system. So we should design a mechanism to maintain multiple requests in the switch memory. We also should make the cache packet served multiple requests once fetched. Otherwise, we should fetch the cache packet from the storage server. But due to the latency gap, it would degrade the performance significantly. We also need to design a cache coherence mechanisms, and we need a mechanism to update the cache entries. But due to the time limit, I'll focus the first two technical challenges in this talk. So this shows how the switch handles the request. Upon receiving the request packet, the switch first checks the cache lookup table. If a cache is a hit, the switch puts the request metadata into the corresponding slot of the request table. After that, the switch drops the request packet. This is totally okay, because the circulating cache packet will serve the stored request metadata soon. So we designed request table as the circular queue data structure, consisting of several register arrays to store request metadata, queue ranks, and front and tail pointers. So this data structure provides per key request queue with small memory footprints. This shows the in-queue operations of the switch. So upon receiving the request packet, the switch checks the lookup table, and if a cache is a hit, the switch returns the cache index. So after that, the switch increases the queue ranks of the corresponding slot, and after that, the switch increases the real pointer. So here, in this example, it goes to 0 because we use the circular queue data structure. After calculating the global index, the switch successfully put the request metadata into the corresponding of the request table. The dequeue operation is quite similar to the in-queue operation, but the dequeue is for cache packets. So upon receiving the circulating cache packet, the switch checks the cache lookup table. So if a cache is a hit, the switch decreases the queue ranks in this case. So after that, the switch increases the front pointer. And similarly, the switch calculated the global index of the request table and retrieve the stored request metadata. So as I explained in the previous slide, the switch pops the request metadata from the request table and updates the packet with the retrieved metadata. So now the cache packet is ready to be ported to the client. But in OrbitCache, we replicated the packet before porting the packet to the client. By replicating the cache packet, the original packet is ported to the client, and the cloned one is recirculated again to serve more requests. So this makes the cache packet served multiple requests once fetched. So we've got two options to implement packet recirculation. So the first one is packet mirroring, and the second one is multicast. Here, we use the multicast functionality because it's much easier to configure. So each multicast group ID specifies a pair of port numbers. So the one is the recirculation port number, and the other one is the port number directed to the client. So let me briefly how the OrbitCache supports variable length keys. So we also use the match action table to implement the cache lookup table. But we use the key hash of 128-bit key hash, so which has a low hash collision probability. So we design a client-side hash collision resolution mechanism. So the client maintains the request key of a pending request. So upon receiving the response packet, the client compared the maintained key with the retrieved key. If they are different, the client sends a correction message to the storage server to get the correct value. In this case, the switch bypassed all of the caching logic so that the client can get the correct value quickly. We have implemented a prototype of OrbitCache using Intel Tofino switch ASIC. We also created the client-server applications in C language. We also use the NVIDIA VMA library for two-sided RDMA color bypass networking. And we use the TomiDS library to implement a simple in-memory key value stores, which was used in the NetCache as well. Our testbed consisting of 8 physical machines. So the first 4 physical machines are clients, and the other 4 machines used to emulate multiple storage servers. We use the per-core partitioning technique, where each thread pinned to a disjoint CPU core represents independent storage server or partitions. By default, we consider 32 storage server with 10 million items, and we preloaded 128 cached items for OrbitCache. So we preloaded 10K items for NetCache. We use the bimodal distribution of Twitter workload. So in this workload, 82% of items are cacheable by NetCache. So we compare our work against the no cache and NetCache. So no cache is the baseline without any cache logic. This result shows that OrbitCache can successfully balance the even highly skewed workload. Unlike OrbitCache, NetCache fails to balance the workload because NetCache cannot cache oversized hot items. And this result shows that the OrbitCache performs the best for diverse workload. So there is some performance fluctuations, but usually the OrbitCache performs the best. So this demonstrates the robustness of OrbitCache to the various workload conditions. For scalability, OrbitCache can maintain high balancing efficiency even with the 64 storage servers, which is enough for a single storage rack. And this result might be interesting because there is a small latency gap between NetCache and OrbitCache when the system load is low. This is not surprising because in OrbitCache, the request should wait until the circulating cache packet serves the stored requested metadata. So that's why there is a microsecond level latency overhead. But you can see that there are huge performance gap between OrbitCache and NetCache, so that's why OrbitCache works. And this result shows the trade-off OrbitCache in terms of a cache size. You can see that after 128 cache entries, the performance is degraded. And as I explained in the previous slide, this is actually expected because if we put too many cache packets, the recirculation port becomes a performance bottleneck. But the small cache effect, O n log n, the n is the number of storage servers, and the number of storage servers is not changed frequently. So usually the cache size is determined quite statically. So this trade-off is quite reasonable. So in conclusion, OrbitCache is the first work that efficiently leverages packet recirculation to balance distributed key value stores. We tried to overcome fundamental hardware limitations by recirculation cache data in the form of a cache packet. So our experimental results demonstrate the efficiency and the robustness of our OrbitCache for highly skewed workload. And we hope that we provide some insight to the research community that built-in switch features like recirculation and the cloning have great potential to make even existing network computer mechanism more effective. So this is the end of my presentation. Thank you for your attention.